In this particular video, we're going to talk about the trigonometric functions for any angle and any size circle. We have previously talked about the trigonometric functions and defined them in terms of a right triangle, but with a right triangle, we're limited to acute angles. We then also looked at the trigonometric functions as it related to the unit circle. In that case, we became able to apply the definitions or the functions to any angle measure, but we're limited to a circle with a radius of 1. So in this particular video, we're going to focus on any angle and any circle, and we're going to actually define those trigonometric functions for any angle for any size circle. And so the formal definition says, let theta be an angle in standard position, and the point P, x comma y, be a point on the terminal side of theta. If r, which is the radius of the circle, equals the square root of x squared plus y squared, is the distance from the center of the circle, which is the origin, to the point x comma y, the 6 trigonometric functions are defined as follow. And it gives you a picture here of what we're talking about. If you draw an angle in standard position, we name that theta, and we draw our radius from the center, which is the origin, out to a point on the circle, which we've named x comma y, then from there we can define the 6 trigonometric functions using kind of the right triangle concepts, where cosine theta is actually the adjacent over the hypotenuse, where the hypotenuse is represented by the radius. The sine is y divided by the radius. The tangent is still y divided by x, and we do stipulate that x cannot be 0. And then remember, these in the second column are reciprocals of the first, where they've just been flipped over. And so we're going to look at how to use these definitions to deal with any size angle and any size circle. So the first example says, let P, which is a point, be -3, -5, be a point on the terminal side of theta. And then it says find each of the 6 trigonometric functions. So we're basically going to use the definitions that we just looked at to find those things. It may help you initially to draw yourself a picture. So we're going to have, if we think about our coordinate plane, okay, so you have x and y, and then we're going to draw an angle that the point on the terminal side is -3, -5. So if I think about where that would be in terms of my number line, let me put some tick marks here. -3, -5 is going to be a point in the third quadrant. We know that the center of my circle is at the origin. The initial side would be on the positive x-axis, and then we rotate around to this angle. And this point here is -3, -5. So the first thing that I need to kind of figure out for this problem is I need to figure the radius, which is the distance between the point that I was given and the center of my circle, which is at the origin 0, 0. And so the formula that we had was the radius is the square root of x squared plus y squared. So guys, it's a straight plug and chug. I'm going to substitute the ordered pair. I have the x value, which is -3, and the y value, which is -5. So I have -3 squared plus -5 squared. It gives me the square root of 9 plus 25, and 9 plus 25 is going to be the square root of 34. Okay, it's the square root of 34. That's a little sloppy. Let me see if I can fix it for you. Okay, square root of 34. Now that cannot be simplified, so we leave it as is. And then we can begin to define the measures of the angle. Okay, the angle is this rotation from the initial side to the terminal side. And so I can define that. The cosine of theta is x over the radius. So I would have -3 over square root 34. But remember, and we've learned this previously, you cannot have a radical in the denominator of the fraction. So we're going to have to rationalize it by multiplying the numerator and the denominator, in this case, by the square root of 34. So I end up with -3 times the square root of 34 divided by 34. Square root 34 times square root 34. The radical goes away. It cancels itself out. All right, then we can do sine of theta, which is y divided by r. Okay, so I would have -5 over square root 34. Again, I cannot have the radical in the denominator, so I multiply the numerator and the denominator by the square root of 34, which ultimately gives me -5 square root 34 divided by 34. And then we have tangent of theta. Tangent of theta is still y divided by x. The y value is -5. The x value is -3, which simplifies a little bit because negative divided by negative is a positive, so I get positive 5/3. And then I have the reciprocal of those three particular functions. Okay, so the reciprocal of cosine is secant theta, which is r divided by x, or in this case, the square root of 34 divided by -3. Now, normally we don't put the negative in the denominator, so I would bring it up to the numerator. So negative square root 34, all divided by 3. The cosecant, which is the reciprocal of sine, the cosecant of theta is the radius divided by y. So we would have the square root of 34 divided by -5. Again, the negative typically does not go in the denominator, so we move it up to the numerator. And then finally, the last one we have the cotangent. The cotangent of theta is x divided by y. So I would have -3 divided by -5, which again simplifies slightly because a negative divided by a negative is a positive. And so I've been able to find those 6 trigonometric functions simply by using the definitions that I was given on the previous slide. There are 6. I'm squaring them off for you. Okay, let's look at another example. It's slightly different. It says, find the exact value of the remaining trigonometric functions of theta if the tangent of theta is 5/12 and the cosine is less than 0. Now, this one's a little bit different because we're probably going to have to use some of our trigonometric identities to help us figure this out. But we need to first think about in which quadrants would we have a tangent that is positive. Well, the tangent would be positive in quadrant 1 because you would have a positive divided by a positive. In quadrant 2, the tangent is negative because you have a negative divided by a positive. In quadrant 3, the tangent is positive because you have a negative divided by a negative. And then in quadrant 4, it's negative again because you have a positive divided by a negative. So I'm either going to be in quadrant 1 or quadrant 3. The other caveat here is that the cosine is less than 0. The idea that it is less than 0 means that it's negative. So if I think about where would the cosine be negative, and the cosine represents the x-coordinate, the x-coordinate is negative in quadrant 3. So ultimately, this angle that I'm going to find, or the measurements I'm going to find, are going to be in quadrant 3. Okay, so that kind of helps me out from the beginning. I know that ultimately I'm going to be in quadrant 3, so I would have my angle. Let me see if I can kind of sketch a rough angle here for you. We have an angle, okay, that comes around here somewhere into quadrant 3. Okay, and we know that the tangent is 5/12. And there's lots of different ways to go about this problem, but again, I'm probably going to wind up using some of my identities. And the first identity that kind of comes to my mind is the Pythagorean identity that 1 plus tangent squared theta equals secant squared. Okay, so I can do a little bit of algebra here and do a substitution. I would have 1 plus 5/12, that's the value of the tangent, squared, equals secant squared theta. Okay, and then I'm going to have 1 whole plus 25. 5 times 5 is 25. 12 times 12 is 144, and that equals secant squared theta. So 1 whole, where I have 144 pieces, plus 25 over 144 gives me 169 over 144, and that's secant squared theta. Okay, so I want secant squared. I'd like to have just plain old secant. So I'm going to take the square root of both sides, and I know that the secant is the reciprocal of the cosine, and I know the cosine is negative, so my secant will also be negative. So the secant of theta is negative 13 over 12. Okay, so there I already have the value of the tangent. Okay, that was given. So there's 1. Okay, I just determined the value of the secant. Once I have the secant, I can use the reciprocal identity because the reciprocal of secant is cosine. Okay, so if I have 1 divided by negative 13 over 12, and I do the reciprocal, I can find that the cosine of theta is negative 12/13. Okay, so that gives me my third angle. From there, again, I've got a couple of options. At that point, I probably would utilize my Pythagorean identity that cosine squared theta plus sine squared theta is 1. And again, I can do some algebra here because cosine is negative 12/13. Square it plus sine squared theta equals 1. So I have 144 over 169 plus sine squared theta equals 1 whole. And I'm going to put that in terms of 1/69 because then I'm going to subtract 144 over 169 from either side to isolate the sine squared. So I have sine squared theta equals 169 minus 144 is 25 over 169. I'm then going to square root both sides, and I may have to think about whether the sign is positive or negative. So I'm going to have the sine of theta equals 5 over 13. We know we're in the third quadrant, and in the third quadrant, the sign is also negative. So my sine of theta is going to actually be negative 5 over 13. So now I have the sine. So there's number 4. To get number 5, I remember that the sine is the reciprocal for cosecant. So cosecant is 1 over sine. So I would have 1 divided by negative 5/13, which ultimately gives me negative 13 over 5. So the cosecant of theta is negative 13 over 5. And I've got one more. And the one that's missing is my cotangent, which I guess I could have done first because cotangent, if you'll remember, is the reciprocal of the tangent. I already have the tangent. It was given. So I'm going to have 12 over 5. Okay, becomes 12 over 5. Okay, so there's the last one. So that gets us all 6 of the 6 trigonometric functions. We were initially given one and an additional condition. From that, we were able to find all the other trigonometric functions using the Pythagorean identities, reciprocal identities, and things that we learned in a previous lesson. All right, let's check out another one. Sometimes when you want to do angles that are more than 360 degrees or they're not a quadrantial angle, you want to use what's called reference angles. So to evaluate functions that have values that are greater than 90 degrees, or if you have a negative angle, we may want to use what's called a reference angle. And the definition of a reference angle is if you have a non-acute angle in standard position that lies in a quadrant, the reference angle is the positive acute angle formed by the terminal side and the x-axis. And I think it'll make more sense when I draw a picture here for you. So let me see if I can sketch you a picture. If we wanted to find the reference angle for 170 degrees. Okay, so if I draw a picture of that angle in the coordinate plane in standard position. So my vertex is on the origin, the initial side is on the positive x-axis, and I rotate around to 170 degrees, I would have this angle. Okay, and so the reference angle is actually the angle that's formed between the terminal side and the x-axis. So it would be this angle right here. Okay, now we know if we get all the way around to the negative x-axis, we've gone 180 degrees. So if I subtract to get this reference angle, which we call theta prime, to get theta prime, we would do 180 degrees minus 170 degrees. So my reference angle is 10 degrees, which is an acute angle, and it makes it a little bit easier for finding the particular values of that particular angle. So if we have 565 degrees, okay, 565 degrees, let's think about what it would look like. Again, if we draw our angle on our coordinate grid, let's see if I can make this a little bit bigger. In standard form, where you have your vertex on the origin, the initial side on the positive x-axis, and then we're going to rotate positively 565 degrees. So we go a full revolution, which is 360, and then we have to go some more to get to 565. We rotate around to 205 degrees more. So that angle would be 565 degrees, which is in the third quadrant. So again, when you start thinking about the reference angle is created between the terminal side and the x-axis, the closest x-axis. Okay, so that would be this angle here. Well, to find that angle, I've gone past the horizontal, which is 180 degrees. So theta prime, which would be my reference angle, would be 565 degrees minus the full revolution, okay, minus 180 degrees, because we had gone just past 180 degrees. So 565 minus 360, which was the full revolution, minus the 180, which is our straight line, gives me a reference angle of 25 degrees. Okay, be sure you subtract off that revolution, okay, because we went a full revolution all the way around. That's kind of tricky. All right, then the third one is, negative 250 degrees. So if I draw my picture off over here to the side, okay, the fact that it's negative lets me know that I'm going to rotate in a clockwise direction. I have my initial side on the positive x-axis with the vertex on the origin, and this time I'm going to rotate clockwise, and I'm going to go 250. So we go 90, 180. I'm not quite going to go all the way back up, straight up, because that would be 270, and I'm looking for negative 250 degrees. Now again, remember, I'm looking for a positive angle. Okay, so I want to think about what this angle would be had I rotated positively. So if I'd rotated positively, I'd have gone 90 degrees and a little bit more to get there. So I was 20 degrees shy, so I'd have 90 plus 20. So if I'd rotated positively, 110 degrees is the same as, negative 250 degrees is the same as a positive 110 degrees. But again, remember, I'm looking for that reference angle, and the reference angle goes from the terminal side to the x-axis. So I'm actually needing this measurement here. Okay, so I didn't make it all of the way from 280. So this would be theta prime. It really helps if you'll look at the picture. So theta prime, the easiest thing to do would be to say, okay, I didn't make it all the way around to 180, and I'm going to subtract 110 degrees, which gives me a 70-degree angle. You could also do negative 250 degrees plus 180, which will give you negative 70, and then you can do it again. You just have to keep rotating. Now you can also create reference angles with radians. You're probably not as familiar with radians as you are with degrees, but let's see if we can do a couple of these. Okay, so we've got 7 pi fourths. Okay, so again, we want to think about, and it may help you to kind of look at your unit circle. 7 pi fourths would be, you go 1 pi fourths, 2 pi fourths, 3 pi fourths, 4 pi fourths, 5 pi fourths, 6 pi fourths, 7 pi fourths is over here in the fourth quadrant. So here is 7 pi fourths. Okay. I'm looking for that reference angle, and again, the reference angle goes from the terminal side to the x-axis. So my reference angle would be theta prime. I'm not quite a full revolution around. A full revolution would be 2 pi. So if I take the 2 pi and subtract 7 pi fourths, that's going to give me the reference angle. 2 pi in terms of fourths would be 8 pi fourths minus 7 pi fourths. So my reference angle would be pi fourths. And then I just have to adjust the sign, the SIGN, based upon where I'm located on the unit circle, or in which quadrant I'm located. All right, negative 17 pi thirds. Let's see. I'll go off over here to this side and draw this one. Okay, so we're going to do negative 17 pi thirds. Okay, if we think about it, in terms of thirds, I would start at 0, and a full revolution is 2 pi, which would be 6 pi thirds. Okay, so if I think about drawing my reference angle, and I want to do 17 pi thirds, if I go one full revolution, I've gone 6. A second full revolution, I've gone 12. I can't go 6 again. Okay, so there would be 17 pi thirds. Okay, again, I'm looking for the reference angle. The reference angle occurs between the terminal side and the positive x-axis, okay, which is going to give me, this is theta prime. Okay, so I've got 17 pi thirds, and I'm not quite a full revolution around again. That third revolution would have taken me to 17 or to 18 pi thirds. So if I think about it, I've gone 18, I could have gone 18 pi thirds, but I'm really shy of that. I'm 17 pi thirds, so I have pi thirds. So my reference angle is pi thirds. And one of the reasons you want to use reference angles is because if you can learn the values in quadrant 1 of the unit circle, then you can use the reference angles to help you find the quantity values. For example, let me show you. If I ask you to find the sine of 300 degrees, well, you may not know the sine of 300 degrees right off the top of your head. But if we look at the graph and think about the reference angle for this particular function, okay, so if I have vertex on the origin, initial side on the positive x-axis, and I rotate, let's see, 90, 180, 270, 30 degrees. Okay, so there's my 300-degree angle. But then I find my reference angle. My reference angle is between the terminal side and the x-axis. I'm not quite a full revolution, so that would be 360 degrees minus the 300 degrees that I did rotate. So my reference angle is 60 degrees. So the sine of 300 degrees is the same as the sine of 60 degrees, which I've committed to memory from my unit circle. And from my unit circle, the sine of 60 degrees is the square root of 3 over 2. Now I need to think about it because I'm in quadrant 4. In quadrant 4, the sine, the value of the sine sin is going to be negative. So the answer here should be negative square root 3 over 2. Okay, so if we think about the next one, the tangent of 420 degrees. Okay, so again, it may help you to kind of get a picture going on here of 420 degrees. With our, let's see, vertex on the origin, initial side on the positive x-axis, we'd go 90, 180, 270, 360, and 60 more. Okay, to get to 420 degrees. So I've rotated past the 360. So again, between the terminal side and the x-axis, we have our reference angle. So I have 420 degrees minus the full revolution of 360, which gives me a value of 60. So the tangent of 420 is the same as the tangent of 60 degrees. Now the tangent of 60 degrees, I hopefully have learned that the tangent of 60 degrees is the square root of 3. I'm in the first quadrant, and in the first quadrant, the tangent is positive. So I'd have positive square root of 3. And again, you can do the same thing with if you have pies or if you have radian measures. Let's see if we can do one quick example for radian measure. Okay, so if we do cosecant of 7 pi sixth, okay, if I put my angle in standard form, seven pi sixth, I would go halfway would be 3, here's 6, and then a little bit more would make 7. So there's 7 pi 6. And again, I may not know 7 pi 6 off the top of my head, but if I use the reference angle, terminal side to the positive axis, okay, there's theta prime. So I've gone just a little bit past pi. So if I take 7 pi 6 minus 1 whole pi, that's going to give me pi sixth. So cosecant of 7 pi sixth is the same as the cosecant of pi sixth. Now the cosecant is the reciprocal of sine. The sine of pi sixth is 1/2, and so the reciprocal would be 2. So the value of the cosecant at pi sixth is 2. Now again, I have to think about the quadrant I'm in. I'm in quadrant 3, and in quadrant 3, the sine is negative, which means the cosecant would be negative. So my answer is ultimately negative.